Okay, so now I want to talk a little bit about an example reaction template. Um, this is sort of what's happening in the Cynthia program under the hood. Here we have kind of our flashcard. Here, this monic reaction is sort of shown in the retrosynthetic direction. We have our product over here annotated with all of these different sort of atom labels, and here are all the possible functional groups at every position. And then we take this back to our amine, our aldehyde, and our nucleophilic ketone. In terms of the actual template itself, just to sort of walk through some of these things, we have a reaction ID. So the folks in Grabowski's team sort of coded this with a unique identifier for each reaction. It has a name. And then here is sort of the way computers typically will represent molecules using these types of string formats. So here there's something called a smart string. A smart string essentially is a way to represent a sort of two-dimensional chemical structure as a one-dimensional line of text. And the way that this text is formatted is it's very context-specific and focuses on sort of different functional groups. So each one of these little brackets represents kind of a functional group, and they're all sort of connected in the way that's specified in this string. So the idea is that you can kind of translate between chemical structures and smart strings, and this can be really useful for looking at, what are the functional groups that are being reacted with in this transformation. This also has a list of protecting groups shown here. And they've also coded in a list of incompatible groups as well, just to keep track of things that maybe don't fly with this reaction type. And as I mentioned before, there are some references down here as well, which is, I think, pretty useful when using a program like this. All right, so now I want to talk a little bit about these template-free approaches. So as sort of an alternative to teaching implicitly or explicitly teaching a program, these sort of reaction flashcards, one of these sort of new emerging ways for teaching a program synthetic chemistry is to use these template-free approaches, where instead of looking at this chemical structure transformation on the top, actually Paul Wender and Vijay Panda in 2017 tried to essentially approach this problem as a language translation problem. And what they did is they said, well, if we can convert our chemical structures to something called a SMILE string, which is kind of like a smart string, but it's essentially just converting this into one-dimensional text. And in theory, you can sort of translate text back to structure seamlessly. And they thought, let's train a neural network to try to translate, in a retrosynthetic sense, products to reactants. And we're not going to teach it anything about what an oxidation is. It doesn't know what atoms are. It's just going to try to translate like English to French, for example. That's sort of the analogy. And so that's sort of the approach. And it actually works pretty well. The performance is similar, I think, to some of these templated approaches, but there are some issues. One of the benefits of this approach is that it's much computationally cheaper for larger data sets, because you can imagine it doesn't have to sort of run through every possible reaction and say, does this apply here? Does this apply here? Which can be computationally expensive. So it's sort of just treating this as a translation problem. Another advantage is that all atoms are sort of mapped in the starting material and product. So unlike a template, which maybe just myopically focuses in on the ketone that's changing in a Grignard addition, here we're translating the whole molecule sort of piece for piece. And that can be really helpful for maybe certain long-range effects or certain subtleties that are sort of baked into the entire molecular structure, rather than just looking at the functional group that's changing. There are some issues, though, that arise from the sort of SMILE syntax. And so sometimes, it ends up translating things into garbage, which don't have any real physical meaning. And if you try to translate this back into a chemical structure, you get sort of an error. So this is sort of a work in progress, but I think people think there's a lot of promise in this area as well. Some limitations of computer-based retrosynthesis are the following. If we consider something like this reaction tree on the left, this is sort of just a screenshot from a Cynthia run. If we think about starting with some sort of target in the middle and then branching out our disconnections from there, you can imagine, right, that the problem kind of grows exponentially. If we start with 10 possible disconnections, and then for each of those disconnections, there's another 10, well, after 5 or 6 rounds, you have millions of different possibilities, and the computer has to sort of keep track of all of these. So you get what Corey called a combinatorial explosion of retrosynthesis possibilities, which can be kind of overwhelming to evaluate and enumerate. So one of the things that's sort of done is usually computer programs will, after maybe 5 or 6 rounds, start to cull all of the possibilities and prioritize which of these disconnections, which of these branches are the most promising, and then sort of not pursue the ones that seem least promising. So there's some sort of trade-offs there. Another area where there are some trade-offs is when you think about how to teach the computer different reactions. So you can imagine there are some trade-offs with how general or how specific of a flashcard you create for the program. If you think about an amide bond forming step, right? You make this as general as possible, any amine coming together with any acid chloride to make an amide bond. One sort of downside of that is that it's maybe not going to be sensitive to, more specific limitations, right? The computer's then not going to know that, well, maybe if you have a really bulky R1 group and a really bulky R2 group, this might not be such a favorable reaction, for example. And so that can be one limitation of a really general conception of a reaction. On the other hand, if you make the reaction, I think, too specific and say, okay, now we're going to teach a reaction for just alkyl substituted acid chlorides and amines, then you have to generate a lot of different reaction flashcards for each reaction class. And so there's some sort of trade-offs there with how you conceive of a reaction. Another downside is, as we mentioned, I think over and over again, the computer only knows what you teach it. And so in that sense, we shouldn't really expect any kind of like new reactions from retrosynthesis programs. It's only going to use what it knows in the database. And what it knows in the database is only what's published in the literature. So I think when people look to, retrosynthesis programs as a source for kind of inspiration of new ideas or new reactivity, I think it doesn't do that very well, unfortunately. So we can't really expect sort of new academically interesting things from this area. And as we talked about, there's a sort of popularity bias of really common reactions and how things are sort of biased towards, some of the more well-trodden reactions when it suggests things in a retrosynthesis. Okay, so now moving on to this next section. I think I should move a little bit more quickly, but how does a program then prioritize disconnections once it's generated a series of different possibilities and precursors? So I think this sort of raises an interesting question of, in general, what makes a good disconnection, right? You all have probably spent the class in the semester so far talking about, Corey's retrosynthesis rules and sort of, his principles for, what makes a strategically good disconnection. But I think in general, and especially as it relates to computer programs, right, the best disconnections are the ones that are kind of the most simplifying. So you can start with something that's really complex, and we want to end with something that's really simple. And, in computer speak, I think this is fairly straightforward. If we try to represent this molecule as a smile string, sort of just this series of numbers and letters, the length of the string gets shorter as you have things that are simpler. So some programs are even just guided by that really crude metric of make the textual representation of the molecule shorter in length in the retrosynthesis direction. But sometimes it's a little bit more nuanced than that in our own work, right? And for academics, the best disconnection might also be the one that maybe teaches the chemistry community something new. So I think when we think about how computers think about this problem, it can sometimes diverge a little bit from our own motivations when we try to sort of push the boundaries in synthesis. Cynthia's scoring function, when it sort of ranks different disconnections, is really sort of geared towards making disconnections that will result in precursors that have a fewer number of atoms and a fewer number of rings. But I think where this sometimes breaks down is sometimes that will lead us into places where an easier solution might be viable. And sometimes molecular complexity is not always the best way to sort of guide retrosynthesis in a computer program. So I want to use this to sort of highlight these two different kinds of complexity, which is sort of, maybe this is getting into semantics, but I think there are some interesting subtleties here that can be really instructive. So when we think about molecular complexity, there's structural complexity and there's synthetic complexity. Structural complexity is essentially, I think, what we typically think about when we look at a complex molecule and we say, what makes this complex, right? It has a certain number of quaternary centers, maybe it has a number of stereocenters, or it has lots of rings. And structural complexity essentially is a function of these inherent molecular features. On the other hand, there's synthetic complexity, which is a little bit different. And this is essentially a function of synthetic accessibility, right? How many steps does it take to make a molecule? How hard is it to make in the laboratory? These two things can sometimes converge. I think it's maybe intuitive that for really complex molecules, like not a lot of natural products, there's a lot of structural complexity and they're really challenging to make. So these two things are kind of aligned. But on the other hand, there are some examples where that isn't necessarily the case. So if we think about this compound here, right, in the steroid vein of things, we can see that if we were to try to analyze its structural complexity, we might say it's reasonably structurally complex. You know, it has a number of rings, it has some stereocenters, and it has some quaternary centers. But perhaps we all know, right, intuitively, that this is only one oxidation away from something that's really cheap, cholesterol. And so we would say that this compound is actually synthetically very simple, really easy to prepare in the laboratory, even though from a structural standpoint, we might say this has a number of rings. So if we just use structural complexity as a metric for a retrosynthesis program, you know, being guided in its thinking, it might start to try to break this down into, you know, linear precursors or simpler, you know, single ring fragments, when we want a computer algorithm to be able to think, oh, this is only one oxidation away from cholesterol. So how do we do that? How do we measure something like synthetic complexity if it's so useful? Well, I think, unfortunately, you would have to kind of generate a full retrosynthesis, right, for each target to actually access or to actually evaluate, right, its synthetic complexity. And even further, this has to be like validated in the laboratory to decide, okay, this compound takes 6 steps to make, this compound takes 5 steps to make. And that sort of, I don't know, defeats the purpose of trying to decide which disconnection is best if you have to actually go and make each precursor to like evaluate whether this is a synthetically, you know, least complex direction. And so one of the ways that's been developed around this is to use sort of estimation tools to sort of guess how synthetically complex something is. And so something that's been done by Connor Coley and coworkers is to train a neural network, a machine learning algorithm on the Reaxys database in order for it to kind of learn the kinds of molecules that are synthetically simple and take only a couple steps to make, and the kind of molecules that are synthetically complex and take a few more steps to make. And so what they did is they trained this on all these reactions. You can see that, you know, in this type of schema, A and B go in a reaction to make C. And so if you were to sort of rank the synthetic complexity of each of these, the product C is going to have a higher synthetic complexity than either of the reactants A or B. And so if you do this for millions of reactions, the neural network starts to get sort of an implicit sense of the kinds of compounds that typically are products and the types of compounds that typically are reactants. It doesn't have any explicit knowledge of commercially available starting materials, but just sort of implicitly learns this from studying the literature. And this actually works quite well. They validated against some other scores and some sort of chemist user rankings. And it turns out that this can actually be quite useful when trying to decide, you know, whether something is easy or hard to make. All right, so now I want to give a little bit of a demo to sort of highlight some of these tools. So let me quick switch my sharing to something else. So I'm going to share my whole desktop, and hopefully this works okay. All right, so here I just want to sort of, everyone can see this okay? Just want to make sure.
Yes.
Okay, great, thanks. So here are sort of drawn out just as an example molecule we'll play around with. You know, this is Paxlovid, this is Pfizer's COVID drug. And if we want to use this in a sort of computer tool, sometimes you can draw them in just like you would in SciFinder. But sometimes it's useful to use, you know, our SMILES encoding as a sort of one-dimensional string representation of the molecule. So in ChemDrive, we can just do this by going to Edit, Copy As, and SMILES, and then we can use this in our demo. So this is ascos.mit.edu. It's a sort of open source, free to use web app, which can be really handy. It's hosted at MIT, so anyone can use it. And there are lots of these modules that are really interesting to play around with. So I encourage everyone to sort of check this out if you're interested in how this might be useful for your own research. Here's this SC score, this synthetic complexity score that we just talked about. So they've hosted this neural net result on this server. And if you just plug in the SMILE string of your molecule, it'll score it for you. So it's kind of interesting. If you want to play around with this can be useful. But I want to use this demo to sort of go to this interactive path planning module. So hopefully this gives everyone a sense of, again, how retrosynthesis is working under the hood for a computer program, and sort of the step-by-step path planning. Normally in a retrosynthesis program, this is all done automatically, and you sort of get finalized routes results at the end. But this is sort of the step-by-step version of this. So you can see we plugged this in, only took a few seconds. Here's our target compound, Paxlovid, and you can see that it's generated these different disconnections. Now, Paxlovid is just a sort of tripeptide, so a lot of these disconnections are fairly intuitive. We can sort of disconnect amide bonds into amines and carboxylic acids. And then here you can also see that each of these different disconnections has been ranked by the program as well. So it sort of decided that this is the best disconnection. It's turned the sort of cyano group in the reverse direction into a primary amide, which actually happens to be what Pfizer does in their synthesis of this molecule. So that's kind of interesting as well. And then at each stage, we can kind of expand these nodes one by one to sort of build out this tree if we decide we want to sort of pursue the top results of this retrosynthesis. So the computer is working, it's sort of thinking, and it's just going to continue the sort of node expansion over and over again. All right, so I think that's all I kind of wanted to show here. I guess I should pause at this point and sort of ask, like, are there any questions or